have just taken the 8085 microprocessor and we have studied various things about 8085 microprocessor, like its internal details, that is the architecture, how that microprocessor is constructed, how the data movement is organized. So that is what we studied in architecture. Then we studied the programming model. After programming model, we studied how to program various subparts of this 8085 microprocessor. Like we studied how to program the internal registers, externally interfaced memory, stack inside the externally interfaced memory, how to program the interrupts. And in today's session, what we are going to do is we will see a generic method of connecting the various peripherals, that is input output devices, to 8085. Now peripherals can be of various types. They could be simply the externally interfaced memory, or it could be a keyboard, a mouse, and a display unit, which is not TFT as in today's case. It might be a simple LED circuit or 7-segment display, etc. So in today's lecture, we are going to see general methods of connecting input-output devices to microprocessor 8085, and we will see some standard devices in some lectures which can be connected to computers of 8085 and 8086 family. So there are various standard ICs, integrated circuits, which can be connected to 8085 to serve various purposes, right? So that is the aim of today's lecture. And of course, with input output, there will be some separate set of commands which is used for making input output. So that is what we are also going to see together with the timing diagrams of 8085, right? Now, before going to that, let us also discuss this chart of commands that we have seen on the last turn. On the last turn, we saw that to be able to study the timing diagram, there were three things that we studied there. First was instruction cycle, second was machine cycle, and third was the T states. So these were the three categorizations or three sub-categorizations of how a complete instruction is executed, right? And there we said that opcode fetch step, this opcode fetch step could take 4T or 6T states, right? So I gave you a list. This was a list of commands where you had got either 4T commands or 60 states, right? So for the commands that are listed here, you will be having 60 states. So before beginning today's lecture, let us now discuss that how some of the commands are taking 60 states and how some of the commands are taking 40 states. So the list of the command that is shown here, it will take 60 states. So let me take an example of this statement, which is first of all call statement, right? So this call statement is going to take 18T states. So can somebody point out how those 18T states will be taken? Can somebody just count the number of which machine cycles will be used? Why these 18T states in all total will be taken? I mean, 60 states will be consumed for opcode fetch, but what are the other machine cycles that will be used for this call statement? Can somebody point this out? Okay, I haven't started the recording, so let me start the recording first. So can somebody point out why is it taking these 18T states? Okay, so call is a statement after which an address is usually written. So call and then some address, and then that address will be of 16 bits, right? So the call statement in itself will consume 3 bytes. This will consume 3 bytes, one for call and 2 for the address which is written after that. So to be able to load this complete statement from the externally interfaced memory to inside the microprocessor, you will require opcode fetch and 2 operand fetch cycles. So for opcode fetch, you are getting 6 T states because it falls in this list. And for operand fetch, you will be having 3 T states plus another 3 T states because the operand is 2 byte address. So 6 plus 3 plus 3. it will make it 12. So that is there. And then after this statement has been loaded into the inside of the microprocessor from the external memory, the purpose of this call instruction is first of all to put the return address onto the stack. So that return address will be put onto the stack. So you will be needing two memory write cycles. Two memory write cycles will be required there. So that is why you will have this 3t states plus 3t states, right? So 6 more will be there. So 12 were earlier and 6 were here. So 12 plus 6 will be 18t states will be required for the call statement, right? So that is the purpose of this call statement. But the point here was to demonstrate another category of call instructions, which is called as conditional call statements, right? So the call is simply a call statement. You will simply write call call, and after that there will be some address. However, there could be another kind of call statements where you call a subroutine when certain condition inside microprocessor is satisfied, right? For example, if you consider this zero flag, if zero flag is set, then you want to call some subroutine. So for that you have a statement called as CZ, and then after that there is an address. CZ means call when zero, or CNZ, call when no zero is there, right? So those are called as conditional call statements, and after that the format remains the same. You will write CZ in place of this call statement, and you will write the address. So here an interesting thing to note is that sometimes these conditional call statements will take 18t states, as we have discussed just now, and sometimes it will take 90 states when a false condition occurs for that. For example, if you are using the statement CZ colon 0, so if the carry flag is set to 0, then of course the things will be normally going on, and as we discussed, it will be taking 18 t states. But when the things are not normally going on, in that case, that is when the false condition is there, I mean when carry flag is not 0, in that case 90 states will be taken. So let us discuss how these 90 states are taken. So first of all, when call instruction is to be executed, whether it is conditional call or normal call, it has to be loaded from the externally interfaced memory to the inside of the microprocessor. So obviously, this is a 3-byte statement, and you will be requiring one opcode fetch. You will be requiring one opcode fetch and two operand fetch. But here the condition is that your zero flag is not set. So if zero flag is not set, so what will happen is through opcode fetch statement, only CZ statement out of this call statement, only CZ statement will be loaded from external memory to the inside of the microprocessor, and it will consume 60 states, right? And since the zero flag is not set, so loading another 2 bytes and decoding them, etc., is not necessary. So in that case, these idle machine cycles will be done by the system, and 6 plus 3, it will be 90 states only. Because if this condition happens to be false, then there is no point of decoding the other 2 bytes and issuing the necessary instructions, etc. So there will be no point of doing that. So only 3t states will be consumed next. So 6 plus 3 will become 90 states, right? So that's what is going to happen. That is why some of the statements that you see here, they have got two types of call statements. And the simulator that we are using, that is Jubin's simulator, it will not give you these two kinds of t states. Whether it is a conditional call or a normal call, it will always show 18 t states. It will go with the maximum number of t states that can be taken by an instruction. So that is one glitch there. So calculating number of t states when conditional call or conditional return statements are there, you have to apply your own brain to see if the condition has been true or not, right? So this was one point that I wanted to make about the list that we saw on the last lecture. And now let's talk about the input output. IO means input output here, right? So in 8085, input output devices can be connected in two ways. Those two ways are input output mapped input output, and the second is memory mapped input output. So these are the two ways in which these input output devices may be connected to 8085 microprocessor, right? So
Excuse me,
that's what
sir.
we are going. Yeah, tell me.
Sir, can you explain once again call conditional?
I have explained this CZ function, call conditional. So what do you want me to tell again? Call function or a conditional call?
No, sir, call conditional. How it takes 18 timing signal and 9 timing signal.
Is this true condition clear to you? I have explained it for call function. It is similar to that, AT&T states.
Yes, sir.
So
Yes, sir.
conditional call can be executed sometimes and it cannot be executed sometimes. When it is true, it will be fully executed, and when it is not true, it will not be fully executed, right? So if it is fully true, I mean, if you are using the CZ statement, call when zero is there. So if zero flag is set, then this call will be executed normally and the subroutine will be called. So that way it will be taking AT&T state in a way similar to the unconditional call statement. Is this up to this part? Is it clear to you?
Yes, sir.
And sometimes it might happen that the zero flag is not set, but CZ statement has something written after that. So call on zero and there is some address. But since that has not happened, the zero flag is not set, so that call will not be executed fully, right? Because the condition happens to be false. Zero flag is not set. So in that case, what will happen is since this statement is still written in the externally interfaced memory, so it will be taken from the externally interfaced memory to the inside of microprocessor. So the first byte is for CZ statement. Is it or is it not? CZ statement.
Yes, sir.
So CZ will be loaded from external memory to the inside of microprocessor. Now, the timing instructions for that will be generated by seeing the carry flag. But carry flag has not been set. Since carry flag has not been set, the additional 2 bytes which are there in the memory, even if they are brought into the microprocessor, there is no purpose of decoding them and generating the appropriate machine cycles, etc. So there is no purpose of that. So only additional 3T states will be executed, and that will correspond to idle machine cycle, right? So 6 plus 3 will be 9 in that case. Not 18 T states will be executed, but only 9 T states will be executed. Is it clear?
Yes, sir.
So we will also see an example of this in laboratory session. Both of the types of call statement will be there, and we will actually calculate how much time the program takes when these two different conditions are there, when zero flag is set or not set, or for that matters for any conditional call statement, if the condition is executed once and if it is not executed once. So what amount of time does program take? That we will see in the laboratory session, right? Now, the next thing that we are talking about is connecting the externally interfaced devices to the microprocessor. So every device is essentially an input-output device. So input-output device can be connected to the microprocessor and in two ways, right? The first way that we will study is memory mapped input-output. And the second way is input-output mapped input-output. So let us first understand what these two ways mean and how useful will they be for our purpose. So memory mapped input output. It simply means that you have a capability of attaching a full 64 byte kilobyte memory to 8085 microprocessor. But it seldom happens. You might have noticed it in your mobile phones also that you purchase a mobile phone. It has got suppose 4 GB of RAMs and 128 GB of memory, but it can be expanded to maybe 256 GBs of memory, right? So what do we mean by expanded? That is, we are not using the full memory capacity. We are attaching only some portion of memory and we are leaving some portion of memory. So this usually happens in processors. You have got a processor and suppose this 8085 has got a 64 kilobyte memory which can be at max externally interfaced, but we seldom use 64 kilobytes of memory. And in those times, maybe 16 kilobyte of memory is sufficient for your programs to be executed. Since memory chips are very costly, so 16 kilobyte, if it is sufficient, we will only be attaching the 16 kilobytes, and rest of the remaining memory space, memory address space is vacant. So in that vacant space, we happen to connect our input output devices, right? So, these input output devices, processor does not know whether it is a memory or it is an input output device. For processors, from processor's perspective, whatever is connected to microprocessor is a device which can take data or give data, right? So this is what only processor thinks about whatever is connected to the processor. So in the section of memory, you will attach, since it has got a full capacity of 64 kilobytes, so you might attach some of the actual memory chip and some of the input output devices, right? So that's what you can do. But for processor, everything will be treated as memory cells only. Because even if it is an input output device, what will it do? It will try to transfer some data or it will try to get some data. So for processor, it is again just a memory. It's just a memory cell which is trying to get some data. So since there are 64 kilobytes of externally interfaced memory locations, and if you do not connect any external memory to the microprocessor, if you only connect input output devices, so how many memory devices can be connected to this processor? Theoretically, theoretically you can have 64 kilobyte, that is 2 raised to the power of 16 memory devices connected to this microprocessor in the memory input memory mapped input output mode, right? So but that is not possible because if you want the processor to operate, you need to have at least some external memory where your programs are written. So in that way only your processor will be able to operate. So some basic memory is mandatory, and after that you can use the space for attaching your uh, input output devices. So in today's computer also, if you're using a laptop or mobile phone at home, the external devices that you connect to your laptop are probably two or three. You have a keyboard, you have a mouse, you have a USB drive, and you might have a CD DVD ROM. So these are 4 or 5 devices that at max can be connected to your microprocessor. But if you see theoretically, the number for 8085 is 2 raised to the power of 16, and in modern computers, of course, it will be more, but they are seldom used, right? So this is what we mean by memory mapped input output. And the second thing is input output mapped input outputs. So this is a pure input output mode where input output devices are connected in input output mapped mode. Here the external devices, they are directly connected to the data bus, and I mean the data portion of the external devices will be directly connected to the data bus. Sorry. And the address space that is used there, it will be interfaced through a external hardware. So we will see an example how to connect these input output mapped devices through input output mapped IO. And the difference between these two is simply that when you will program the computer, and if you have attached input output device through memory mapped input output mode. So I told you that for processor everything is a memory cell, right? So the same commands which we were using to deal with memory, that is MOV command or maybe MVI command or LDAX command, STAX command, the same commands will be used in this mode. However, for IO mapped input output, you will be using two different commands, which is in and out. So in for taking the data from the external world to the microprocessor, and out for doing the other thing. So these are the two different modes which are available. Now let us see these modes separately. So I'm not going to pay any attention to memory mapped input output because it is exactly similar to interfacing a memory. We will be mainly focusing on IO mapped input output. We first need to understand what it is and how in and out commands are used, what is the amount of time those commands take, and what are their timing diagrams. So that's what we are going to study in IO mapped input output section, right? So let me begin by taking this example. So are the fonts clearly visible on their screen, on your screen for this diagram?
Yes, sir. A little zoom out.
Okay, so I will just zoom it out once I explain you this every section. So here you can see that this is the device which you want to connect to your microprocessor, right? So you can just see only this particular portion. This portion you can see. So here you can see there are S0 to S7. There are these 8 switches which are attached, right? And through wires they are connected to this buffer IC. So this is 74LS244 is a buffer IC, and onto the one side of this buffer IC, this device is connected. This device is connected. The data portion of this device is connected, and to the other side of this IC, you have the data bus of 8085. Data bus could take some data from this device. So this can be thought of as, a keyboard or something which is giving you data. Maybe it is a keyboard or something else. So whatever switches will be on here, their values will be treated as 1, and rest everything will be treated as 0. Don't bother about these resistors. These resistors are just a part of electronic circuit to provide appropriate voltages, because if you have studied this electronics sometime in your course, you might be able to notice that there is a +5 voltage here, and there are these resistors. And if the switch is connected, there will be a different voltage at this particular point, which will be treated as 1 voltage. And if it is not connected, then whatever voltage is available, which will be definitely 5 volt, it will be treated as 0 voltage level. So +1 and 0, they are given different voltage levels in electronics. So even if you neglect this particular portion, that is perfectly fine. The only thing to understand here is this is a source of data, and whatever switch is closed, it will be treated as 1, and whatever switch is not closed, it will be treated as 0. And through this IC, they are connected to data bus. That data will be transferred to the data bus, and that can be transferred only when this IC is activated. So this IC will be activated when this OE, or the output enable signal, is activated. This OE is a low signal. So it is an active low signal. So when the value on this particular line, will be 0, this IC will be activated, and whatever is the status of these lines, or these 8 bits or 1 byte, it will be exactly copied to the data bus. So that is what is going to happen. So I will relate it to the IO mapped input output. First of all, just understand the circuitry, right? So now if you see, we need to have a 0 value here. And for that purpose, what we need to do is, this is an external device which you have connected to your microprocessor's data bus, and you are supposed to read some data from this externally interfaced device. And here you are treating this as an input device because it is giving you some data. Now, as I told you, that this IC will be only activated when this chip is activated. So this chip will be activated when this signal is 0. So when do I want this chip to be activated? It will be decided by the microprocessor. Suppose an in or out command is there in program. So what my microprocessor will do is it will have some address, and that address should be used to enable this particular chip. So that is what is there. If you connect any device in the input-output mapped input-output mode, then obviously the data will be available on the data bus, which is available here. And to be able to read that data, there should be this signal, enable signal, which should be able to activate this IC and copy the data here. And how is that enable signal working? That enable signal should be determined solely from the address lines, of microprocessor. Now, an important thing to understand in this microprocessor is that if you are connecting the devices in input-output mapped input-output mode, at that particular time, the maximum number of addresses that can be used is equal to the size of the data bus. Size 2 raised to the power of size of the data bus. What is the size of data bus here? 8 bits. And 2 raised to the power of 8 will be 256. So for any microprocessor, there are two ways, as we have seen in this. First is input output mapped input output, and second is memory mapped input output. In memory mapped input output, the theoretical number of devices which can be connected to the microprocessor is 2 raised to the power of 16. So this is determined by the size of address bus. And for the first one, it will be determined by the size of data bus. That is 2 raised to the power of 8 number of IO mapped input output devices can be connected. So it happens to be 256, right? So you can notice here that for this hardware circuitry there are these A0 to A7 pins, right? So these are address lines A0 to A7. Rest address lines from A8 to A15, they are just a duplicate version of A0 to A7. So in IO mapped input output mode, you give the address bus not the complete 16-bit address but only 8-bit address, and that 8-bit address is duplicated onto the lower order bus as well as the higher order byte of the bus. So you can use any pins, either A0 to A7, or you may also use pins from A8 to A15 for the purposes of addresses. And it is also important to note that A8 to A15 will contain addresses. I mean, even after your first tick of the clock, when you are trying to read something through input-output command, because we already know that latching mechanism, we can use an external IC to be able to latch the addresses, right? So that is attached in the lower byte. So both ways, I mean, any set of the combinations can be used. So you can see that A0 to A7 are connected here. And what we are trying to do is, to this particular device that you see here, input device, we have attached an address of 80 in hexadecimal, 80 in hexadecimal. And when these lines display an address of 80, in that case only, this Y0 output will be made as 0. This is also active low IC. So if 80 address is being put here, in that case only this Y0 output will be equal to 0. And we want the final signal here to be 0. So for that, this particular thing should also be equal to 0, because this is a OR gate. And if OR gate is there, if both of the inputs are 1 or any of the inputs is 1, the output will be 1. But to activate this tri-state buffer IC, we will be needing this value to be 0. So if this value is supposed to be 0, both of these signals are to be 0. And both of these signals will be 0 when an address of 80 in hexadecimal is put onto this. Then this will be Y0 will be 0. We will see how it is 0. And for this to be 0, you can see that these two signals should also be 0, because this is again OR gate. So for these two signals to be 0, this read bar signal will be 0. And if the read bar signal is 0, that means it is already activated. So you are trying to read something, which is obviously true, because from this particular section you are taking the data and you are trying to read it inside the data bus. So obviously you are trying to read something. The second signal should also be 0, which means before this NOT gate, this signal should be 1. So if IO/M bar is equal to 1, that means we are dealing with the input output device. We are dealing with the input output device. So the IO/M bar is 1, that means we are dealing with the input output device. Read bar signal is 0, that means we are reading the things. So that way this thing will be 0, and we want this to be 0. So how will this become 0? We need to understand what this decoder is, right? So I will just quickly show you the diagram for that decoder. So that decoder 74LS138 is like this. We do not need to remember its structure even. For the purposes of explanation, we just need to see it. So here the useful pins will be address input pins 1, 2, 3, and then G2A bar, G2B bar, and this G1 pin, right? And the outputs you can see they are from Y0, Y1, Y2, etc. So we are only concerned with this particular output. And for every IC, there is a truth table. For every IC, there is a truth table. So the connections that we want to have are these 4, 5, and 6, which is G2A bar, G2B bar, and G1. And these connections A, B, C. So first these 3, and then second these 3 in that particular order will be taken for our purposes. So if you see the truth table of this, then this E1 bar, E2 bar, they correspond to G1A, G2A bar, and E3 is G0, and A0, A1, and A2, and output is Y0. So we want this output Y0 And there are other outputs also, but we want this output y0 to be 0, that is low value, not high value. So we are concerned about this. So you can see that for this combination, when the output is low, you have all of the values as low in the input, only one value is high, which happens to be this E3 value, right? So that E3 value, if you are able to see it, that E3 value, it corresponds to this G1. That E3 value, it corresponds to this particular G1. So you need to apply this as 1 and rest everything as 0. Rest everything will be applied as 0 here, right? So if you see in this particular diagram, this G will be applied as 1 and rest everything will be 0. That is A0 to A6, everything will be 0 because this G2 bar is a combination of these three address pins. So since there is a OR gate, and if you want a 0 output at the OR gate, so all of these three pins should also be 0. So if A7 is 1 and rest everything is 0, what is the combination that you have got in binary? 1 triple 0 and then 4 times 0, which means 8 0 in hexadecimal. So if all of these pins have that address as input, in that case y0 will become equal to 0, and in that case you can see that this signal will also become 0 if this input is 0. So this IC will be activated and your data can be transferred from the input side to the outputs. I mean from the externally interfaced peripheral to the data bus of the microprocessor, and that is how it will be inputted. So here you can see that if you want to take input from an external device, you actually have to interface an additional hardware. This additional hardware is needed to be introduced to be able to activate or deactivate a particular IC, right? And that is why whenever you connect your keyboard or mouse, etc., they can be connected through USB or whatever variety of ports are available. So they have their separate kind of, I mean, if it is a USB, definitely it will be driving the power from that USB port only. But if you see the COM ports also in your computer, then there is a separate kind of hardware in the older computers which you use to interface for keyboard, etc., and they used to draw power from there, right? So this additional circuit is needed to be able to enable or disable this buffer. So this was valid for 80H. So how many addresses can you have there? So definitely 256 devices can be connected. So you can have addresses in hexadecimal from 00 to FF. So 256 complete addresses can be there in terms of this input-output mapped input-output mode. So when there will be a command in 80H in your program, so this 80H will be transferred here on the address bus, both on the lower and the higher order byte, and the circuitry will be activated and your data will be read onto the data bus and it will come inside the accumulator directly, right? So this is going to happen. In a similar way, we have got this output device here. So here what we are trying to do is inside the microprocessor, we now want to try to display something. So here we have connected a series of LEDs from L1 to L8. So you have 8 LED bulbs, or you have, so not LED bulbs, you have 8 LEDs, light emitting diodes. So you can supply, for example, if you consider only one LED, then you can supply a value of 1 to it so that it becomes on, and you can supply a value of 0 to it so that it becomes off. And since there is a combination of 8 different LEDs, so you can put them on or off depending upon whatever number you want to display. So any combination can be made out of those 8 LEDs and a number could be displayed in binary form. So that is what we are treating as our display for now. So this display essentially is the output device because microprocessor will be giving it some data to display, and accordingly the bits will be set or reset to display that number, right? So in this case, we have taken the address for attaching this device as 81H. So this is your 81H address, and this this hardware that you see here, whenever 81H will be attached here, these circuits will be activated and this chip will be activated. So I'm not going to again explain the logic for this hardware that is attached here. You can actually see the truth table for the circuit that I have shown you earlier, and you can figure out that whenever there is 81H attached here, in that case only this Y1 output will be it will be becoming activated, and this gate that you see here, this is a XOR gate. So this will correspondingly activate this particular IC. And when this will activate this IC, you can see that the data bus of 8085 is connected here. So this data bus, it will be copying its data to these particular Q0 to Q7 lines, and it will be a combination of ones and zeros. So whatever is the combination, it will be given to this set of LEDs, and they will correspondingly light up or switch off. So that number will be displayed in binary to the user. So is this thing clear to you? How to take input and output in terms of hardware from 8085 microprocessor? Is this clear to everyone? Yes or no?
Yes, sir.
Yes, sir.
Okay, so this is a very simple circuit.
For the output it's 81, for the input it's 80.
In this example, you might take any addresses in the range from 00 to FF, right? If you choose to have an address of suppose 55H, so the corresponding hardware will change, right? The corresponding hardware will change because it's not that in older computers you will attach. See, in today's computers you have got many ports for attaching various things, right? So you can attach through USB ports many items on the single thing. But in older computers, you need to fix your plan first. You have a 8085 microprocessor, and whatever peripherals you want to attach, you will decide that okay, these are the peripherals which will be connected to my device forever. So you accordingly design this interfacing hardware, which will enable your peripheral to use the 8085 microprocessor. So these are fixed. So 81H in this example is fixed for this particular kind of display. But however, if you want to attach it at some different address, suppose 55H, so this hardware should accordingly change, and that way it should be attached. So 81H is not a fixed address. It can be any address of your choice. So
that means we can find out if that it is different. We can find out by truth table if
yeah,
it is
you
another
have
IC.
you have this truth table, so you can figure out what you want to achieve and how you want to activate or deactivate your IC, right? So you can see that for every output
No,
there is only
it can
one
be a different IC. No, that I'm asking. You said this
which IC?
truth. This truth table can vary, na? You said
This truth, I didn't say that this truth table can vary,
no,
but
no, not
yeah.
this. You
Uh-huh.
said that IC, the IC not where we
This
input
IC.
A0 to decoder. Sorry,
No.
this circuit
Mm-hmm.
which you are using to activate the buffer.
Mm-hmm.
This is always same, or this is always this can vary.
See, this complete portion will vary depending upon how you want to activate. For example, if you choose an address of 55H, currently this IC is configured, since this is an input device, so this IC is configured for 80H, right? So suppose it is configured for 55H, right? And 5 in hexadecimal will mean what? 101, I mean 0101 for 4-bit combination. So you have this address 0101 and then 0101. So for this particular case, when we had 80, only this G signal should be activated and rest everything should be deactivated. But now if you want to attach it at 55 location, so you have to have a 1 here, so you will be applying a NOT gate here because this is configured for 80. So ultimately that 55 should be converted to 80 first for being attaching it here, so that only G is activated. So you have to use appropriate NOT gates if any input happens to be 1 here, right? Because this is now configured for 80 only. Or otherwise you have to go to the truth table and you have to see for which combination you are getting this 55 here, and accordingly the hardware should be interfaced. So you can see for every output Y0, Y1, it only happens low one number of time. So for every combination it will be high, but only for one particular combination it will remain as low, right? So accordingly, either by reading this truth table or by making various NOT gates, etc. in this hardware, you have to activate or deactivate it, right? So we will see some examples in laboratory where we will change these addresses and change the structure of this IC. And this is one disadvantage of attaching devices in this mode. That is, there is an additional hardware requirement which will be dependent on the port number. Port number means the place at which you are connecting your input output device. So this will be one disadvantage with this particular thing, right? So this hardware
Yes.
structure will completely change according to the address that you have used, right? Now, let me list out some differences between memory mapped and input-output mapped input-output scheme. So we already know that in memory mapped scheme, the address is 16-bit, thus A0 to A15 lines are used to generate the device address. That's what we have already seen for when we programmed the microprocessor. However, for IO mapped, the address is only of 8 bits. That is, the size is equal to only data bus, and that is why A0 to A7 lines will be used, or alternatively, you might use A8 to A15 lines, and both of these will be containing a duplicate copy of the address, right? So when we use this memory mapped input output command, the similar activation signals, memory read and memory write, were used to activate or read and write the input output devices, because ultimately you are connecting your devices in the memory space only. However, for IO mapped input output, you are having the signal input output read and input output write control signals, they are used. Then the commands that will be used in memory mapped mode are simple: LDA, STA, LDAX, STAX, then move instruction in HL pointer as a HL register pair as a pointer. So that way you will be transferring data to and from memory. So whatever you have attached at that particular memory location will be dealt with these commands, right? The commands which you usually used. However, for this input output mapped mode, you have these two commands, in and out. So let me just show you an example of this in and out command in Jubin simulator, and then we will talk further on this chart. So let's see Jubin simulator and one good example for learning input output command, and you will see that it is fairly simple. Yeah, so let me just zoom this portion out. Okay, so this is a simple program where what we are trying to do is, there is some data which we want to take as input, and there is some data which we want to give as output. But now this time we are using the input output mapped input output mode. So first of all, let us read the program, and then we will make appropriate changes in memory. So begin 7500H means our code will begin to execute from 7500. Org 7500H means whatever is written after this statement will be written after this location in the externally interfaced memory, and that will be treated as our code. So that's what we mean here. And now what is code? What this code is doing? What this code is doing in 09H, in 09H. So port number 09, that is a input output device which is having an address of 09. It will have 1 byte data. That 1 byte data will be taken from that input output device. That will be an input device because we are taking input from that. So from that input device, you will take that 1 byte data and keep it in accumulator, right? Then in the next step, from that accumulator, you will copy it to L register, right? For later use. So you will copy it to L register. In the next step, you will move a data of 03H into accumulator. And our intention is to copy this data to a device, to an externally interfaced device, which is now an output device. And we want to copy this data 03 into that. So first of all, it has to be moved to accumulator. And through this out 20H command, this 03 data will be copied from accumulator to that particular external device whose address happens to be 20H or whose port number happens to be 20H, and the system is halted. Is the program clear to everyone?
Yes, sir.
So it's a very simple program, a pilot program. So let me now first configure my system so that it can be used with this program setting. So first of all, we are trying to take input from 09H. So here on this tab, you can see this register array, then this memory array. If you want to show the entire memory, then this is a huge memory. And you can see that this is the memory side. And this is the devices side. Devices means now you can have 256 input output devices connected in input output mapped input output scheme. So here you have got these devices. So these are 256 devices. The addresses begins from 00 to finally here FF, right? So this is F0 and this is F. So this is completely FF address. So these are 256 devices. And at 09, so we are trying to take the input. So let us see where is 09. This is 00 and this is 9. So let me just change some data here. Let me keep it as 55. Right. So a data of 55 is kept here. We want to read this data through this in command into the accumulator and put it into the L register. That's what we want to do. So let me come back to the register array, assemble this program, and let me try to run this. So Alt right, and the first statement is run. That is, wait a minute. There is no data in this. Let me check. I have done some mistake here. Let me again check it. So at this address 09H, I have to keep some data. Okay, the data is gone here. So 00 and this is 9. So 09H, let me keep some data, which is 55. Yeah. So this data is there. Okay, after assembling, I need to keep my data. So this is assembled, and after assembling, let me keep some data here, which is 55H. So now this data is there, and let me now try to execute it one by one. So Alt right. So first statement has been executed. Now you can see in the register array that accumulator now contains a value of 55. So it has been taken from the externally interfaced device at an address of 0009, and the data was 55 there. Some input device was connected there, and we copied the data 55 into the accumulator of the system, and now we can do anything with this data. So in the next statement, what we have done is we have copied this data to the L register. So it is copied here for our later use. Now our intention is to move a value of 03 into the accumulator and copy it to an output device whose address is 20. So you can see that in this devices, this 20 address is written here, 20, and this is 0. So this is 20 address. After execution of the next command, the data that will be kept at this 20 address is 3, because in accumulator we have moved a value of 3. So let me run this code, and you will be able to see that this has now a value of 3 here, and then the system will be simply halted. So this is a very simple program to demonstrate the input-output commands when the devices are connected in I/O mapped input-output mode, right? So this is what we were discussing. So in and out commands will be used in input-output mode. Then the data transfer between any register, data transfer is between any register and I/O. If you're talking about memory mapped input-output device, so the data transfer is between any internal register and the input-output device in this mode. However, in input-output mapped input-output mode, the data transfer is between accumulator and I/O device. So the default register is accumulator, so that is why accumulator is being used there. Then the maximum number of devices in this mode is 65536, which is 2 raised to the power of 16 theoretically. And for this particular mode, they will be 256. Then the execution speed of LDA, STA, etc. You all know how to calculate it. So sometimes it will be different for LDA, for move, etc. So LDA, STA, they will consume 13 T states. Move statements will consume 70 states. But the execution speed is 10 T states for this in and out. So for in and out, it is fixed. It will be 10 T states, right? So in a moment, we will discuss these T states also, why these are 10 and what machine cycles are used there. Then decoding 16-bit address may require more hardware, and decoding 8-bit address will require less hardware. Obviously, when I showed it to you in these older diagrams, that if there is an 8-bit address, you will be using a 8-bit decoder, right? However, if there is a 16-bit address and you want to connect an input-output device to be able to activate or deactivate it, more number of hardware is required, right? So, which is very obvious for digital logic students. So these are the points of differences between these two modes: memory mapped input-output and input-output mapped input-output. Now let's talk something about the execution state, which is 10T states in and out command, right? So again, let us see the same program. We have both commands here, in command also and out commands also. So can somebody guess out of the machine cycles which are now shown on the screen, which machine cycles will be used in and out command? And how many T states will be consumed? Any guesses? Everyone is sleeping.
No, sir.
Okay, so how much, I mean, in and then we write after that some address. So in itself will consume only 1 byte and address will also consume 1 byte because the address can have a maximum value of FF. So it can consume maximum 1 byte. So how many bytes will be consumed by in or out statement together with the address? 2 bytes will be consumed. So to be able to read it from the externally interfaced memory, how many machine cycles will you be having? One should be the opcode fetch and another should be the operand fetch. So since it does not fall into this list, so 4T states will be required for opcode fetch and 3T states will be required for the operand fetch. So 4 plus 3 T states are required, right? So 7 T states are required. After fetching that command, after fetching the in and 20H command inside the microprocessor, do we need to do anything else that deals with this memory? Yes or no?
IO.
Input output read.
You have
Input
to read
output.
this input output read. So 3T states will be required more. So that way 10T states will be required. So whether it is in instruction or out instruction, 10T states will be required. And now here, if you just simply double click on this T states, you can see the appropriate cycles will be displayed there. One is opcode fetch cycle, machine cycle. Another is not memory read. This is again operand fetch. We have discussed that this is a glitch in this software. They have read operand fetch as memory read cycle only, which is technically the same thing, but the name is different. So it is opcode fetch. Then there is a IO read cycle. And as we have correctly guessed that there will be 4T states for opcode fetch. Then for memory read cycle, there will be 3T states. And for IO read, there will be 3T states. We have already discussed this opcode fetch and operand fetch cycle for various commands. The only new portion here is this IO read cycle. So in IO read cycle, you can see that it is trying to read some particular port and the port address is same on both of the address and data bus, right? So port address is 75 here. Here also the port address is 75, right? So that address is same here. So that is one point to note, that address and data bus are duplicated when you are trying to connect your devices in IO mapped IO mode. And that again this ELE will be enabled. Obviously this IO slash M bar should be equal to made 1 because now we are dealing with the memory. And S0 and S1 should be appropriately set to indicate a IO read cycle. So you can see from the truth table that one of them will have a value of 0 and other will have a value of 1 to make it as IO read cycle. And since you are reading, so this read signal should be activated. That means it should be made low and write should be deactivated. So this is a very simple thing. You can now understand these timing diagrams also. And some instructions might have more number of machine cycles. So you can also see it. I mean, after this, they will be attached. So this is just a simple description of how to connect your input output devices to the microprocessor 8085. And now I will be taking one more lecture on 8085 to illustrate you the complete command set that is available with 8085. Because in essence, what we have done up till now is we have studied the microprocessor from hardware as well as software perspective. Now what we need to do is we need to connect the external devices, input output devices. And for that, we have already made some roadmap today where we saw how devices can be connected. They are treated as memory elements. Whatever those devices are, they are simply treated as memory elements. Because for computer, any device, if it is connected, it will either give some data or take some data, right? It depends how that data is taken, whether it is from keyboard or from a switch, and how it is displayed, whether it is an actual monitor or it is a set of LEDs. So it depends upon the structure of that hardware, what it do with that data which it has got from the computer or it has given to the computer. So that's irrelevant. Everything is treated as just your memory device. So we are now not going to discuss some sophisticated devices which can be connected to 8085. I will keep that discussion for some later time when we will complete this 8086 microprocessor. Then we will discuss some common devices which can be connected to 8085 and 8086 to assemble a computer system, a complete microcomputer system, right? And that time it will be more relevant. So for now, I will be taking one more lecture on 8085 to discuss the addressing modes and the complete instruction set of 8085. And we will pause our studies of 8085 there. We will study 8086 in the same manner, and then we will discuss the keyboard, monitor, etc. of that time which could be connected to these devices to make it a complete micro computer system. So this week, the laboratory that you are going to have will be the last laboratory for 8085, and we will again try some concepts that we have discussed in lecture. And after the completion of that lab, you have to submit file in that particular lab, right? So any doubts for today's session? Anyone, if you have any doubts, you may discuss now, or we again have a laboratory session where we will again see every matter of this kind, and we will have some experiments there to elaborately explain the concepts that we have developed today. Okay, so I have already downloaded the attendance list, so I'm closing this session for today.
Thank you, sir.
Thank you, sir.